for partial fractions, comma, x. Maple demands that you say specifically what letter it is that is supposed to be your variable. The reason for that is that this way, you, instead of having number coefficients, you might have A and B letters, and this would, and a variable that's x, and then this would give you partial fractions using the letters as your coefficients. And you see the 3 over x minus 2 plus 2 over x minus 3 that we did working by hand. And so then if you look, say, at problem 3 that we just did, convert x plus 4 over x plus 1 square, par frac, and you see the 3 over x plus 1 square plus 1 over x plus 1. Your graphing calculators will, well, I guess I can't say for sure that all will, but most of them will do partial fractions. If you have one, you can see whether it wants to do them or not. Meanwhile, look at something like 21, where you have quadratic factors. I was saying that in algebra, you can take any polynomial and you can factor it down to a product of linear and what we call irreducible quadratic factors. This is irreducible in that if you were trying to factor this, you'd be involved with the square root of minus 1 with I. The use of the letter I for the square root of minus 1 goes back to Euler, in case you're interested in history of mathematics. He's the one that said we'll use I. The electrical engineers, of course, wish he had said J, but we weren't doing electricity in Euler's time, other than Benjamin Franklin out trying to electrocute himself with the kite and the key, and so on. So, notice also this one is a definite integral. So what we have, you see, if you have a linear factor, you'll have A over the linear factor. And for each quadratic factor, you can have two terms in your numerator in general. Some unknown letter B times x, which you notice is a degree lower in power than the denominator, and then the c over x squared plus 1. So what I'm saying then is that for this problem, there are three numbers, a, b, and c, where a over x plus 1, bx over x squared plus 1, and c over x squared plus 1 will add to give you this fraction. You could write this part as two separate fractions so that there'd be 3 altogether, or you can do it this way, which is what I'm more familiar with doing, and it's what the book's doing. So regardless of what you're going to do or not do to get B and C, I would say at least get your A with poles and residues, so that if you are going to solve simultaneous equations for B and C, you're only doing 2 equations and 2 unknowns instead of 3 equations and 3 unknowns. So for the A, then, multiplied by its denominator to get your residue, And where its denominator is 0, which is at -1, is its pole. You do poles and residues for each linear factor exactly like here, regardless of whether you have quadratic factors or not, and regardless of whether you have repeated linear factors or not. So if you were, in other words, to multiply through by x plus 1, over here it would cancel, and what you see is your residue, 1 over x squared plus 1. The pole is at -1, so put that in, and you get a half. So A is a half, no matter what you do or don't do to get B and C. So now the most you'll have to do is 2 equations and 2 unknowns for B and C if you're going to follow the book, where they would say find any x you want other than -1, because you can't divide by 0, and put in 2 different values for x. Notice you'll also have to put whatever you chose there, and you can solve for B and C. Actually, you see, pretty easy would be to use x equals 0, because then the B is gone and you're just solving for C. So you could do that. Use poles and residues to get that A is a half. So then you have a half to put there. Then if you put 0 in, that removes the B from that equation. The only unknown will be the C, and then you'd have 0 there, and 0 there, there, and there. So you could do that. And then if you know A and C, take some other number like 1 and put that in for x, and you can get the B. So you can do it that way pretty easy. Or you can do this with poles and residues. Because if you're trying to get bx plus c, so you have to work with it together, because it's the one denominator, multiply through by that denominator, which will give you, when you cancel over here, what you see as your residue, 1 over x plus 1. So the residue would be this, and you see your pole would be what makes that denominator 0, which is I, square root of -1, right? And so your residue is this, and your pole is I. So your residue at your pole removes this, because you've multiplied through really by this denominator when you got your residue. So you have A times 0, and then over here you have bx plus c and I. So this will get you B and C together. The only price that you pay is that you're working with complex numbers. This is why you took Math 108, learned to work with complex numbers. Then did some more in Math 143 or 147. So put the I in here, and you have 1 over 1 plus I. Put the I there, and you have BI plus C. So to match complex numbers, they both have to be in what you call standard form in Math 108, which means that you don't have the I in the denominator. You have a real denominator. So if you have this kind of thing, if you remember your Math 108, what you do is multiply top and bottom by the conjugate. Remember, the conjugate has the same terms with the opposite sign in the middle. So I multiply top and bottom by the conjugate, then I multiply these two. The product of conjugates gives you real numbers. You have this times this, which is the 1 square, and then this times that, which is minus I squared. I squared is minus 1, so you have minus 1, so you have 2. So finally, what this is, denominator 2, you have a half minus a half I equals the real number C plus the real number B times I. So then you match the real coefficients, so C is a half, and you match the imaginary coefficients. Okay? This is all Math 108 or Math 143, it's just that you've probably kind of forgotten it. But you can get your two unknowns that way by matching up complex numbers, or you can do substitutions, whichever you want to do. So finally, we have C and B. So then the original integral is the half over x plus 1, and then the 1/2 for the C over x squared plus 1, and the minus 1/2 for the B over x squared plus 1. And the B is times x. So you have 3 terms. So this first one is going to give you a half log x plus 1. This next one, what I've done, you see I have x squared plus 1. If I'm going to call that u, then I want 2x dx for my du. So I've multiplied and divided by a 2. That's this 2 and that one. So that if this is u, that's du. So the integral is going to be this minus 1/4 log x squared plus 1. And then for the third term, I have the 1 over x squared plus 1 squared, and that'll be arctangent. So I have my half log, my 1/4 log x squared plus 1, and I have half arctangent. So this integral with the 2x, as I made it over x squared plus 1, is really a u substitution problem, but rather than writing it with u and changing my limits, I just figured out that it would be the log x squared plus 1 and left the original variable in the original limits so that these all match. And so then I have a half log 2 minus a 1/4 log 2 from here, and a half the arctangent 1 is pi over 4. And then log 1 is 0, log 1 is 0, and arctangent of 0 is 0. So then you clean this up and you get what the book has. Let's see, I'm not sure, did we do 21 with the maple? Turn the page to see. No, I did 22, but, and I did 18, I didn't do 21, but. So, before we go on to 22, is there any question here on 21?